You ever notice on a hurricane, sometimes the roof just comes off? So if there's like winds that are really, really strong and you're, drinking your green tea in your house, waking up at 4 o'clock, or you're at work filing papers because you got that nice job that your mom gave you and now you're making that guap. So imagine you being in a building and there's wind blowing above the house. So wind has to go up and then over again. And if the wind is strong enough, it can actually lift the roof right off. So if you ever watch any of those YouTube videos with hurricanes, you can see people's roofs just come right off. And the reason for that is because of Bernoulli's equation that we'll look at here. It's going to be the difference in pressure. When you have a difference in pressure, you can generate a force. Another example of this difference in pressure that you've probably seen before is if you're in your house and all the windows are closed except for the one in your room. If you ever open the door to your room, it's sometimes either really easy or difficult depending on the pressure difference between your house and the door. And if you try shutting the door while your window's open and all the other windows are closed in your house, the door will slam shut. And again, that's because of this pressure differential. And the other example that we talked about in the last lecture, if you woke up for it and watched it, was there's this yellow marking on a subway station. So when you walk onto the subway platform, there's a yellow, I think called that, of course. So where was I going with this? So when you walk on the subway, usually there's a yellow line area where they tell you not to stand. You have to stand beneath that. And that's because when a subway car moves like this, there's going to be air that's also moving this way. So if you're standing here and the subway is going this way, when the subway moves through here, it's going to push the air in a certain direction with a velocity. And so the air with a velocity always has lower pressure than air with air. The higher the velocity the air has, the lower the pressure. And so if it's the train, then the gap between you and the train, and behind you is more air, there's going to be air pressure that's going to be less between you and the train because the train is pushing the air this way. And it's going to be less to the pressure behind you. And air pressure always moves from high pressure to low pressure. So if a train is moving really fast, there's going to be a really big difference between the pressure behind you and the pressure in front of you, which kind of pushes you forward, which is why they have that yellow line marking there, because they don't want you to hit the train or go into the train tracks as the train passes you because of that pressure differential. And we're going to use that same pressure differential to explain why roofs can come right off the top of your house. So here is our question. We've got a house here. We've got wind blowing at 44.7 meters per second. That's a special number. 44.7 meters per second is 100 miles per hour. So wind is blowing at 100 miles per hour. You can think of this during Hurricane Sandy. And the area of your roof is 200 meters squared. The density of air, not of water it's 1,000 kilograms per meter cubed. For air at sea level, the density is 1.29 kilograms per meter squared. And we've got a pressure 1 here. We've got a pressure 2 here. And what we want to do is figure out, I don't know if you can see that, what we want to do is that because the wind is blowing above, the pressure above the roof is going to be less than the pressure beneath the roof or inside the house. And pressure always moves from high to low, which means there's going to be a force that's going to push the roof upwards. And we want to know how much force that is. Okay? So to do that, we're going to use Bernoulli's equation, which is P1 plus rho g h1 plus 1/2 rho v1 squared is equal to P2 plus rho g h2 plus 1/2 rho v2 squared. So there's Bernoulli's equation, and we're going to figure out what the force is equal to. Okay. So how are we going to do that? We need to know what the pressure differential is. So the difference between the two pressures, that's going to be our goal. A few things. The height right above the roof and right outside of the roof is roughly the same. So we can say that H1 or H2 is roughly going to be H1. So the height here and the height here, the difference between them is negligible, which means this term and this term will cancel out. Something else, there's no velocity inside of the house. So V2 is going to equal 0, which means that term goes away. And so what we're going to do is we're going to write an equation for, well, let's actually write this out first. P1, what's left over, plus 1/2 rho V1 squared, and that's going to equal P2. That's it. That's what we're left with. Now we want to know what the force is that's going up on the roof. How do we solve for the force? Well, if we're talking about it in terms of pressure, force, in this case, we're going to look at the difference in pressure is going to result in a force difference divided by the cross-sectional area. Pressure is always defined as the force divided by the area. And so if we want to know what the force is, it's going to be the pressure difference between the pressure inside versus the pressure outside times the cross-sectional area. Where'd my eraser go? Here we go. So I'm going to erase that. And so what's nice is we don't actually really need to know what the pressure is. We can just solve for P2 minus P1. The difference in pressure is equal to P2 minus P1. So if I bring the P1 to the other side, what I'm left with is 1/2 rho V1 squared. And that's the difference in pressure. Once we have this, we can substitute it into there and solve for the force. And so the force is equal to 1/2 rho V1 squared times the cross-sectional area. So let's plug it in and see what we get. The force that it's going to experience is going to be 1/2 multiplied by the density, which is 1.29 kilograms per meter cubed, multiplied by V1. V1 is 100 miles per hour, or 44.7 meters per second, multiplied by the cross-sectional area. So the area of the roof, not the cross-sectional area, the area of the roof. The area of the roof is 200 meters squared. So what does that equal? It's going to equal 257,700 newtons. Now, what is that? Like, I don't know what that is. We could put it in terms of pounds to make it a little bit easier to understand, because we all understand pounds. So if you do a unit conversion of this into pounds, and we can do that by doing 1 pound is equal to roughly 4.48 newtons. So 1 pound is equal to 4.48 newtons. Is that correct? Or is it 2 point something? I think it's actually 2 point something. So whatever. Let's just leave it in terms of newtons. What you'll end up with is 57. If we do what I just said there, it's going to be equal to 57,500 pounds of force. Some interesting things to take away from this. This is a lot of force. And that's because the area is really big. If the area was really small, then the force would be smaller. So the larger the area, the larger the force is going to be. So you're going to experience this much force on your roof. And if your roof isn't built like well enough to sustain these kinds of winds, it's going to come right off. And it does come off for some people, unfortunately. A few things I wanted to say was that actually, if we just look at delta P, if we just look at this term right here and solve for it, delta P is equal to 1,288 Pascal. So the difference between outside and inside is this much. Is this a lot or small? Well, atmospheric pressure, the atmospheric pressure is equal to 101,300 Pascal. So if you compare atmospheric pressure to the difference in the pressure change, it doesn't seem like a lot. And yet we ended up with 257,000 newtons that was lifting up this way. So even though the difference in pressure doesn't look like it's large, when you multiply it by a large area, such as the area of a roof, you can get a very large force. So there's that question. Let's move on to question 2. Question 2. You didn't think I came unprepared. I don't have to draw out the whole question, did you? Of course not. So here's question 2. We might need this board, so I'll just leave it here. Okay, so in the last question, I know Helen watches these videos later, so she'll see. In the last example, it was Akane's house when she's older and she has her own money. Her house is so crummy that the wind will blow off. But this example, we have Helen's house, and Helen doesn't live with the commoners. She lives all the way on the top of a mountain looking down on people. So when Helen watches this, she'll understand the joke here. Helen's looking down on the people down here, and water has to go to Helen's house. You know, Helen has plumbing because she's rich. So this is your main line of water that goes underground, and that line has to go up this mountain in order for the water to reach Helen's house. Now, the pipes that are in the mountain that are going up have to be significantly smaller than the main pipe that's going this way. Okay, and her house is 100 meters from ground level. That's the other thing here. And at her house, the atmospheric pressure is 2 atmospheric pressures, so 2 ATMs. So that's what the current pressure is at Helen's home. And we want to know how much pressure down here has to be generated, how much pressure has to go through here so that water will go up Helen's house and just stay there. So it's staying there, which means there's no velocity here, which means Helen's faucet is turned off. So no water is going out right here. It's just water that's being stationary right there. We want to know how much pressure it takes right here to keep the water to be stationary there, so that when Helen does open the faucet, water will run through. How much pressure is it down there? So, how do we solve this question? Well, just like with all other questions, we need to write down our Bernoulli equation. So writing down the Bernoulli equation, just like we do with all the other ones, we have P1 plus, what is it, rho G H1 plus 1/2 rho V1 squared, and that has to equal P2 plus rho G H2 plus 1/2 rho V2 squared. Okay, so that's what we have here. What can we do? Well, we're trying to find what pressure 1 is. In our diagram here, if we call H1 0, then H2 would be 100 meters. So let's define H1 as the starting base. And we do that, we get rid of H1. Okay, so far so good. What else can we do? We know that velocity 2, there's no velocity going through here, it's just stationary there. So that's going to equal 0. But something else that's interesting is that velocity 1 is actually going to be 0 as well. Why is that? I can look at the water running through here and compare it to here. We have an equation which states that the velocity at 2 times the area at 2 is equal to the velocity at 1 times the area at 1. So let's say we wanted to solve for the velocity at 1. The velocity at 1 would equal V2 multiplied by A2 divided by A1. Now, if we look at area 1 here and compare it to area 2, this is the cross-sectional area right here compared to the cross-sectional area there. We can say that A1 is much, much, much bigger than A2. And if the denominator is much bigger than the numerator, we can say that V1 is going to be roughly 0 velocity. So V1, gone. And anything else that we can say? Oh, this faucet wasn't moving water here. So because there's no water moving through here, there's no water flow, it's just stationary there. V2, gone. And what we're left with is a really nice equation. We've got P1 is equal to P2 plus rho G H2. And that's the pressure needed just to keep the water up. So if we plug into our values here, we will get 2 atmospheres, ATMs, plus rho, this is water, so it's 1,000 kilograms per meter cubed, multiplied by gravity, which is 9.8 meters per second, multiplied by the height, which is 100 meters. And finally, this is in ATM, atmospheric units, so we need this term in atmospheric units. And we do that by saying 1 ATM, whoa, is equal to 100,000, 1,300 Pascal or Newton meters. So if we do that, then this and the Pascal here will cancel out, and you'll be left with ATMs. And the value you will get is 11.6267 atmospheric units. So that's how much pressure is needed down here in order for the water to be right there. So that's when the faucet is off. But, you know, this is Helen's house we're talking about. The faucet's obviously going to be running. So what I want to know next is, what if the water starts to flow in the house with a speed of 2 meters per second? So if the water is flowing, she turns on one faucet, and it's flowing with the speed, 1 meter per second. What is the change in the pressure? What's going to be the change in pressure when you are now flowing water through here? Let's look at that. So how are we going to write this? We want to know the change in pressure when the faucet is running. So when V2 is equal to 1 meter per second. What's going to be this change in pressure? Meaning how much pressure do you need to add, or how much pressure do you need to take away from the top in order for the faucet to run? So the way we're going to do this is we're going to call the initial pressure that we had. Let's look at, whoa, it's going to fall. Let's look at the initial pressure down here. The initial pressure was given by this equation right here. P1 is equal to P2 plus rho GH2, right? So we'll call that P1 naught. And that's equal to P1 plus rho GH2. That was the initial pressure down there. The final pressure, the new pressure, is going to equal P1 plus rho GH2, just like before, except now water is flowing in object 2. And that's going to be, was this supposed to be P2? Sorry, this is P2. P2, H2, and so this is going to be 1/2 M rho V2 squared, because we're saying V2 is equal to 1 meter per second, not 0. So this was the final. This is the initial pressure at 1. And all we have to do is to find delta P. We take this minus this. So this term will go away. This term will go away. And the change in pressure is going to be given by 1/2 rho V2 squared. And that's going to equal 500 Newton meter squared. So that's how much pressure you need to add. So if this was our pressure before, it's an ATM. You have to add this much pressure in ATM down here in order for the water to flow that way. The other thing you could do is, instead of increasing pressure here, what you could do up here is decrease the pressure there. So whether you increase the pressure here or decrease the pressure here will allow the water to flow at 1 meter per second. And so if we compare that to what's actually happening, so this is the change in pressure. This is how much we need to decrease by. But you have 2 atmospherics of pressure at the top. So 2 atmospherics of pressure is 2 times 101,300 Newton per meter squared. So that's how much pressure is at 2. So if you were to decrease by this amount from this value here, water is going to run. It'll decrease by a little bit, but the water will still run, because this is still a lot of pressure compared to the little bit that you need to get rid of. And so that's that. Well, what if we had changed it? Instead of one faucet running, Helen had her bathtub going, her sink going, her outside garden hose going at the same time. So the amount of fluid that needed to go through the pipe was 5 meters per second instead. So if it were 5 meters per second, well, this would all still stay the same, except the value would change. It would be now equal to 12,500 newtons per meter squared. So you would need a drop of this much in for water to flow. But that's still okay, because this number is still significantly smaller than the atmospheric pressure that's up at that height. So even if you were to lose that much, you would still have enough pressure. You'd still have pressure for water to flow through there. Okay? So that was question 2. Now the last question is airplanos. This one is interesting. I really like this one. I remember when I started student teaching, at a different school, there was another physics teacher who taught there for 8 years, and he was like my master teacher, the one I was observing, sort of like an internship is what we call student teaching. And he was a pretty good guy, pretty knew a lot of things, but one thing he didn't know how to explain was why planes fly. Why do they go up in the air? And it all has to do with pressure differentials. So let's take the look at the wing of an airplane. The wing of an airplane looks something like this. And there's a reason for why the wing of the airplane goes. This is like a side view, a cross-sectional view of the airplane's wing. So why does the wing of the airplane look like that? Well, if the plane is moving, let's say at 134 meters per second in this direction here, so that's V equals that, and 134 meters per second is the same as 300 miles per hour. So if the plane is going at a speed of 300 miles per hour, and let's say we've got these particles here that are stationary. So we could look at it from that point of view, or if you had a person standing on the plane, then these particles are the ones that are moving in this direction at 134 meters per second, and the person on the wingtip is stationary. So that's how we're going to look at it. These particles are moving at this speed, and they're going to hit the wing plane, the wing of the plane. Now, for particles down here, they don't have to intersect with anything. So a particle right here would just go like that, and then be on its other side right here. But for a particle that's hitting this, and this is why planes are shaped this way, it's aerodynamically why they do it this way. A particle right here would hit the surface here, then hit the surface here at the same time, hit the surface here at this time, hit the surface here at this time, here, and then back. And so they're traveling, they're traveling the same x distance because they have to have the same speed. So the particle that was above here and down here, they have to still match. But this particle has to actually go a greater distance. So if it's actually traveling a greater distance to get to here versus the particles that are down here to get to there, we could say that the speed at the top, the speed of the top particles, and then we have the speed of the bottom, and the speed of the particles at the top have to be greater than the speed of the particles at the bottom. And that's because this thing hits this, and then it's going to go like that, and they still have to meet up at the end, the particles at the top and the particles at the bottom. So if we look at it in terms of wind, you'll probably see it in an engineering class. If you take a fluids class, you'd see like a line that goes like that, and then you'd have a line that curves like this, and then goes down. And this is also called laminar flow. And we'll talk about laminar flow in the next class. But this is what it's going to look like. And so you've got the velocity going this way, and you've got the velocity going this way. And the wind velocity down here is going to be some value, 134. Let's call it 134 meters per second, because that doesn't change. But the speed on top, because it's intersecting and it has to go to the top, it's going to have a higher speed. And we're just going to make this up. We'll call it 400 miles per hour. So 400 miles per hour is the same as 197 meters per second. 179. So we've got a velocity at the top and we've got a velocity at the bottom. Okay. So hopefully, I hope you understood that much. Wind that way, wind this way, wind faster at the top, wind slower at the bottom. Remember hold on a second, please. Oh my goodness. I just got one of those phone call scammer people. Whatever. We don't worry about those scammers. So, where were we? So, this is identical to that very first question we did, where we talked about the wind or the speed of the wind at the inside the house versus the speed of the wind outside of the house. And because there was a pressure differential, there was a force to lift the roof off, and that force is called the lift force. And that's what causes a plane to fly. So let's take a look at our picture here of our plane. Let's draw a plane out. How do you draw a plane? I tried drawing one this morning. I thought I did a pretty good job, but everyone's a critic. Actually, that's a terrible plane. That ain't a good plane. Let's do that. That's better. Like that. There we go. We'll have a nose here. That won't be like that. And then we'll have our wings here. Like that. And the area of the wing is 50 meters. So each wing has an area of 50 meters squared. Oops, 50 meters squared. So we've got that. That's going to be our wings. A few things we want to know. Let's write it out. What are the forces acting on this plane here? The ones that we're interested in. Let's assume, actually before that, there are several forces that allow you to go into the air that we can discuss, and we will discuss. One of those forces is the buoyant force. So a balloon is the result of the buoyant force. So the buoyant force is what lifts the balloon up. A rocket, on the other hand, for a rocket to go up, we have the force due to the thrust, the exhaust of the pipe going down, which causes a thrust. For a glider or a paper airplane or even birds, right? And a plane, which is what we're interested in. The reason why a plane can fly is because of the force due to lift. It also has to do with the thrust, but we're going to ignore the thrust force for now. We're only interested in the lift force. So we're going to assume that there's no thrust. It's a plane that's just gliding in the air right now, and no thrust going on. So what does that look like? It's going to be weird because we need air, but we're going to ignore air resistance. So we're going to ignore air resistance, but we need that air. It's so weird to do this question like this, but the end idea is just to figure out what the lift force is. Now, the plane has weight, the force due to gravity of the plane. And that's going to equal 49,400, or do we want to do that? 49,000 newtons, sure. We want to know what the lift force is going to be. Okay? We want to know what the lift force is going to be, and we know that the wing of the plane is doing this. It's going 134 meters per second downwards and 197 meters per second upwards. So we want to know what the lift force for the wing is going to be first. So how are we going to do that? Let's go back to our picture here. The first thing I want to do is write down Bernoulli's equation. So we have P1 plus rho g h1 plus 1/2 rho v1 squared is equal to P2 plus rho g h2 plus 1/2 rho v2 squared. And this is the height, and delta h, let's make this easy on ourselves, is going to be roughly 0. The height from the top part of the wing to the bottom part there's not much difference in height. So it's going to be negligible. If delta h is 0, roughly, then that term goes away. And what are we left with here is we're going to solve for the pressure differential. So we're going to bring P1 to the other side. We're going to bring this term to that side. And we get that P2 minus P1 is going to equal, what are we going to call P1 and P2? Let's say this is the, we're going to call this the bottom. And this side is the top. Okay, so we're comparing the pressure at the top minus the pressure at the bottom, and that's going to equal 1/2 rho, 1/2 rho, 1/2 rho, that comes out, and it's going to be the velocity at the top, the velocity at the, did I do that right? So we bring this to that side, and P2 minus P1 should equal 1/2 rho, the velocity. Let's just write it in terms of top, bottom. We'll just call it that way as well. The velocity at the top squared minus the velocity at the bottom squared. I think I have this backwards, but who cares? We just want the magnitude of delta P anyways. So this is equal to delta P. And so what you can see, because we have this equation, force is equal to delta P times the area. That's going to give us the lift force. This is from that question that we did with the roof. It's going to be delta P times A, but in this case, it's going to be 2 times A because we have a wing here and the wing on the other side. And this is what delta P is equal to. So the force due to the lift is going to equal 1/2. Now let's use the density. Let's use the density at the density of air at sea level. So the density of air at sea level is 1.28. Do I want to write that? I want to write down the equation first, so then I'll write it out. So force lift is going to equal delta P, which is 1/2 rho, V at the top squared minus V at the bottom squared, multiplied by, in this case, 2 times A for each wing. Technically, we could just write it as A, but we'll because I called A in the question A, just one wing, and we have 2 wings, it's 2A. From here, we can plug in our values, so it's going to be 1/2 times 1.29 times the velocity at the top, which is 179 squared, minus the velocity at the bottom, 134 squared, multiplied by 2 times the area, which is 50 meters squared for each wing. And when we plug all of that in, we will get our value of the lift force. And the lift force is going to equal, in this problem, 908 comma 500 newtons. So if you compare the force of gravity versus the force of lift, this plane is going to shoot up into the sky. It's going to accelerate. If these are our only two forces, there's going to be an acceleration in the y direction. Now, how could you increase that acceleration further? Maybe there's wind blowing. If the wind is blowing opposite your direction here, then you'll get an even larger force. But I want to show you something really interesting that we get from this equation here that I don't know if you missed. Look at this equation right here for the lift force. Without the lift force, you can't fly. The lift force depends on the density of air. So as you go up the atmosphere, as you go up in our atmosphere, the density of air gets less and less and less. And in space, the density of air is zero because it's a vacuum. This is why planes can only reach a certain height. The smaller this value is, as you go up in elevation, the smaller the lift force is going to be. And eventually, you're going to reach a point where these two forces, the force lift, is equal to the force of gravity. And when that happens, it doesn't matter how fast you're going. When the lift force is equal to the force of gravity, you can't go any higher. This is why planes don't leave our atmosphere, because they need density of air. They need air. Without that air, you don't go up. And this is why it's weird, but this is why we can't fly on different planets, like the moon. The moon doesn't have any air, or very little of it. So you never see airplanes taking off on the moon and coming back. Instead, when you're in space, you're not going to be concerned with the lift force. You're going to be using the thrust force. And the thrust is what lets you leave the moon, but you wouldn't be able to fly on the moon because there's no air that will let you glide on the moon. And the less air there is, the less you'll be able to fly. So more densely packed gases, like on a planet such as Jupiter, will allow you to fly pretty easy, but your plane will probably crash because of the density of air anyways. But still, it will give you a lot of lift force. And that's that. Hopefully you got an idea of how planes work. You need this lift force. The lift force is generated by a difference in pressure, and that difference in pressure comes from the Bernoulli equation. Something else you may see like this, where you could see it, is in cars. So very fast moving cars will actually, if you go too fast, they'll actually go up. And that's because you're moving so fast that the pressure beneath the car and above the car is so different that you'll generate a lift force. And that's why cars that go really fast, like those funny cars, they're called funny cars, they're drag cars. They'll actually shoot up into the air. They won't like fly forever, but they'll shoot up like that. And so how can you reduce that lift force? Cars, like really, really fast cars, have a thing on the back of their car, which is called a spoiler. And the spoiler creates the opposite pressure. So there'll be more pressure at the top than at the bottom, and it'll try to keep your car grounded. So that all has to do with aerodynamics. And if you decide to become a mechanical engineers deal with moving parts and stuff like that, you would do that. And I guess it would be a specific field in mechanical engineering called aerospace engineering that deals with aerodynamic stuff. So there's that. Okay, so that's it for today's lesson.